This is Chapter 9. I will call it Sections 1 and 2. So if this is Chemistry 1, everything that I want us to cover out of Chapter 9 will be in this one presentation. It is heavily involved in math. You're going to need your calculator and your periodic table packet as we go through this, and try to keep up with calculations, making sure that you get whatever I get when we get to our examples. So there will be several examples of these stoichiometric calculations that you'll need to get into your notes. So stoichiometry, it is the mass relationship between substances in a chemical reaction. So now that we have done chemical reactions in Chapter 8, and it's also based on the mole ratio, and we talked all about moles in Chapter 2, which we jumped from Chapter 3 to Chapter 8. We're going to put all of that together now and do stoichiometry problems. So within all of our stoichiometry problems, the key or the central step of all of these is called a mole ratio. And within the mole ratio, we're using the coefficients. So the coefficients in this example are 2, 1, 2. You're going to use the coefficients as your numbers needed during the mole ratio step. There are 6 different possible mole ratios of this particular problem. For instance, it could be 2 moles of magnesium per 1 mole of oxygen. There's one example. Or maybe 2 moles of magnesium oxide per 2 moles of magnesium. I could keep going and get 6 out of this particular question. It just depends on how my stoichiometry problem is set up and which 2 substances I want to compare. You will learn how to do that. So here's the steps for stoichiometry problems. Step number 1, you must have a balanced equation. And that means if you were given a word description, then you have to come up with a unbalanced equation yourself with all the proper formulas and then balance it. We will identify our known and unknown. The known is the given information in the product. The unknown is, well, what is the question actually asking us to find? And I'll show you the difference between known and unknown as we go through examples. And then we start lining up conversion factors. I'm going to list to you 4 possible conversion factors that you'll see as we're going through stoichiometry problems in this chapter, with the first one being in every single one, and that's our mole ratio. So mole ratio does compare moles to moles of 2 different substances. You've seen molar mass before. It compares moles and grams. The next 2 are going to be new to you. Molarity compares moles in liters of solution, whereas molar volume compares moles in liters of gas. And see what all of these have in common is the mole. So the mole, even what we did in Chapter 3, now we're here in Chapter 9, the mole will be the central step to any of the stoichiometry problems that we do. Now what I'm going to do here is I'm going to take these 4 conversion factors and I'm going to actually set them up as conversion factors so that you can see what they might look like in a grid. So we'll start off with our mole ratio. And again, the mole ratio, that one is key to everything that we do here within stoichiometry. The mole ratio, that is moles of unknown over moles of known. Now, the numbers that are used for the mole ratio, out front, you would have a number here and a number here, and it's always, well, where do you get these numbers from? The numbers that go with the mole ratio are your coefficients within your balanced equation. So when you're making your notes and you write out a C and a C, if you can't remember that means coefficient, then make yourself an extra note in your notes. So C, it's the coefficients within a balanced equation. The next one was molar mass. You have already seen molar mass within Chapter 3. Molar mass is grams per mole. And again, it's understood per 1 mole. And the number that goes with grams comes from the periodic table. So again, you have already seen this one before. That should be nothing new for you. The next one is going to be new, and it is molarity. Molarity, we will use a capital M to denote molarity. And the units that go with molarity are moles per liter. And this is dealing with a solution. That means something in the liquid phase. So a solution. This time in the denominator, it's so many moles per 1 liter. So 1 liter, the 1 goes there. But what number would go with moles on top? This value is typically going to be given within the problem. So the number with moles would be given within the problem, but you might see within a problem something listed like 1.2 capital M NaCl or NaOH. Well, that capital M means moles, and you would just write it down in your notes as 1.2 moles per liter. That's how it translates. And then the last one we were looking at was molar volume. Molar volume is dealing with a gas. So molarity is a solution, something in liquid form. Molar volume is going to be gas. And I can tell you within the problems we're going to do for this chapter, just because I'm going to try not to confuse you too much. If I ever give you a problem that has molarity, then molar volume will not be part of it. If I ever give you a problem dealing with a gas and molar volume is being used, then molarity will not be a part of it. And the reason why I say that is because the units are essentially the same, they're just flipped. So instead of mole per liter like molarity is, it's liter per mole for molar volume. And again, that understood one goes there at the bottom for molar volume. And the special number that we use here for liters is 22.4. 22.4. Later on, when we get to gases, I will explain to you why it's 22.4 specifically, and we'll work out the math with it. But 22.4, that is the volume of a gas, 1 mole of gas. It's STP, or standard temperature and pressure, and I will show you that on another slide too. So there is your information. Everything on this slide, you want to make sure you get down in your notes. I would use some color if you need to. I'll try to keep things color-coded as we go. So heading back to this slide, again, the mole ratio is our core step, and it will be in all problems that we do. The mole ratio is what allows us to move from information about our known substance to our unknown substance. That's also why it's going to be extremely important that you label all of your substances within your grid as you're doing your math. Now, molar volume, we looked at it, the 22.4 liters per mole. Again, if you have 1 mole of a gas at standard temperature and pressure, it will occupy 22.4 liters of space. That is its volume. So that is a standard number that we will use when we're dealing with molar volumes of gases for this chapter. Now, you've seen the boxes before. I am going to redraw all of this, but I'm going to leave off number of particles as we go through everything that I want to go through on here. And these two, yep. Mass to moles, got all of that, but now we're going to add on molarity and molar volume just so you can see those also. So we'll start with the ones that you are used to seeing. So you do have mass measured in grams here. You do have moles, and the unit for moles is the mole. So there you go with your moles. These can go in either direction. The units we said are grams per mole, and it's understood per 1 mole. And if you're finding the mass of a substance, you get that mass off of the periodic table. So if it's the mass of an element, great. If it's the mass of a compound, we've went over how to find molar masses of compounds, so you would show that math work too. Now, Let's go to the box at the top. Again, this can go in either direction. The one that was at the top dealt with molar volume. So molar volume, the units for it were liters per mole, and it was, again, understood per 1 mole, but the number that went with liters was 22.4. So if you're converting between moles and liters of a gas, so this has to be for a gas, then that 22.4 will be used. And our box at the bottom that we added, which can go in either direction, that was molarity. And molarity deals with a solution, so this is something that's going to be in liquid or aqueous form. The units for it were also the liter and the mole, but it's reversed. It's mole per liter, and that's understood per 1 liter. And the number that would have to go with moles here, for any problem that we do, most likely it will actually be given to you in the problem. So if it's given to you in the problem, make sure you change the capital M to its rightful units of mole and liter. There are 2 units with it because you won't see capital M's within our grid. Please make sure you get all of this written down in your notes. Just adding some more of that color, the moles right here. That is the one thing missing. So once you get to that center box as you're doing your conversions and you hit moles, that sets up your mole ratio step. And again, the mole ratio step was moles of unknown over moles of known. And you'll use your coefficients as your numbers that go with each of these. That's from your balanced equation. So if I asked you to convert the mass of one substance to, or let's say the molarity of one substance to the mass of another substance, you would start here with molarity. You would convert to moles. Once you got to moles, you would do the mole ratio step. That would be a second step. And then you could go out to the mass of your unknown substance as a third step. So expect many steps on several of these. So have this handy as we go through some examples. And we're going to try to go through 4 examples now. You need to write the question for every example. Some of you, as I'm checking over your podcasted notes, you're just writing down the work, but you're not writing down the actual questions that go with your work. So that can be a little hard to understand later on. So please write down the question and your work. How many moles of potassium chlorate must decompose in order to produce 9 moles of oxygen gas? So the first thing we start off with is a balanced equation. This one might be a little harder for you, but let's say I did give you the equation KClO3 breaks down into potassium chloride and oxygen gas, and I asked you to go back and balance it. At this point, you should be able to balance an equation like nobody's business. The coefficients would be 2, 2, and 3. Then I would want you to write down all of your given information. So given information here, the only number I see is the 9, and that is 9 moles of oxygen gas. So under oxygen, write 9 moles. That is my known information. I know something about oxygen gas, but my unknown in this problem, it says how many moles of KClO3 must decompose. So my unknown is KClO3. I'm going to put a question mark under it, and it's asking me to solve for moles. So I'm going to put MOL right there. All of our stoichiometry problems will start off with one substance and ask you to convert to a different substance to find out some information. That's going to be the importance of everything that we do here. If I were to ask you on this one, things to write down or to make sure that you get written down within our grid, I want you to put, like we did earlier, you have to put a number. you need to put a unit, and you need to label the substance or compound or element that is given. So I'm just going to put compound right there. And whatever unit and compound is here will be repeated right down here. They will match up. So we are ready to solve this. I want you to be looking back at your chart that you've got with all of your boxes. This is asking us to move from moles to moles. That is a one-step process. We put our given information in first. I know that I have 9 moles of oxygen gas, so I have labeled my number, my unit, and my substance. Moles of oxygen has to be repeated here at the denominator. That is moles of known. Anytime you have moles of known in the denominator, you're automatically going to set up your mole ratio step and put moles of your unknown, that's my question mark, KClO3, moles of unknown in your numerator. The coefficients are used here within my mole ratio step. So I'll put the 3 with our oxygen, the 2 with potassium chlorate. I notice that these units cancel. I'm left with moles of KClO3, and my problem does say find out how many moles of KClO3 must break down or decompose. And I'm ready to do my math. 9 times 2 divided by 3 will give you your answer. This PowerPoint will stick with significant figures for the most part. Again, depending on what class you're in, might not be too picky about the significant figures. Make sure that you can get a final answer of 6 moles of potassium chlorate. Moving on to our next example, we're going to use the same equation, and we're looking at how many grams of potassium chlorate are required to produce 9 liters of oxygen at STP. So if I were to label my given information, I have 9 liters of oxygen, that's gas. Ooh, notice it says at STP here. If you see STP for this chapter, that is a giveaway. You're working with a gas, and more than likely you're going to be dealing with molar volume, which is dealing with a gas. And it says how many grams of KClO3 are required. So our unknown, again, is KClO3. This time, we are moving from liters to grams. If you think about your boxes, you had molar volume here at the top, you had moles right there in the middle, then you had grams. So here's how many steps this problem will be. It will be 1 step to get from molar volume to moles. While we're at moles, that next step has to be your mole ratio. And then your third step, we can finally move to grams. That'll be a third step. So you will have 3 steps in this problem. If you can figure out how many steps your problem's going to be before you ever get started and set up your grid, that's honestly half the battle. And we will continue to follow the units. So we are ready to get started on this. We said that this was going to be 3 steps. Again, I don't count the given as a step. So there's 1, 2, and 3. Label everything that you have. Our given, we have 9 liters of O2. Again, whatever we have here must be repeated right down here, which is liters of O2. Our next box after molar volume or liters is moles, so we do go from liters to moles of O2. Those units match up with molar volume. I see moles, I see liters. And if you go back and you look at your molar volume, it is, I'm trying to make sure I stick with the same units that I was dealing with earlier. It is 22.4 liters per 1 mole. 22.4 liters per 1 mole. And I'm going to go ahead and go over that in case you can't see the 22.4 well. Those units cancel. I'm left with moles of oxygen, which must be repeated at the bottom. So moles of O2. That gets us to our central box, which means ding, ding, ding. It is time for the mole ratio. That's moles of known in the denominator, so moles of unknown must go in the numerator. My unknown is the KClO3. That's where my question mark is at. And it is time to use our coefficients. Again, a 2 goes with KClO3. A 3 goes with the oxygen. There are the coefficients, and those units cancel. I'm left with moles of KClO3, which I have to keep going because I'm trying to get to grams of KClO3. So, again, those units are repeated here at the bottom because I got to get rid of them. And I am moving from the central box, which is moles, out to the left, which is grams. So, grams is going to be right up here at the top. And if you look back at your numbers there, the number that goes with grams is from the periodic table. And you're going to have to calculate the mass of KClO3. Well, as I'm looking at my periodic table, I only have one potassium, that's 39.10. I have one chlorine, which is 35.45, and I have 3 oxygens, each of those at 16. When you do your molar mass calculation, you should get 122.55, and we are ready to do our math. So everything above this line is multiplied. So 9 times 1 times 2 times 122.55. Everything below that line you divide. So divide by 22.4, divide by 3. You can divide by 1. That won't change your answer. And you want to make sure you come up with the proper answer, which is 32.8 grams of KClO3. 32.8 grams of KClO3. Again, if I'm thinking of the boxes that I have, starting off with liters, I moved to moles. Once I got to moles, I had to do my mole ratio step, and then I went from moles to grams. So there are the 3 boxes you're seeing there, and that mole ratio step is key to every problem that we do. It will be within your stoichiometry problem at some point. In this problem, they do not give you enough information to know what the full reaction is, so I am going to go ahead and write down the reaction for you. This one will be copper plus silver nitrate. And a single replacement reaction will give you silver plus copper 2 nitrate. And again, you don't know which version of copper it is, but this is going to be copper 2 nitrate. You would have to go back and balance this reaction. So when you get your coefficients in there, it would be 1, 2, 2, 1 as your balanced reaction. If I am labeling my given information, I only see 12 grams of copper given. So we've got 12 grams of copper. And it wants to know how many grams of silver will be formed. So we're going from grams to grams. If you think about your boxes, you're starting off with grams. You have to go to moles. That's 1 step. While you're at moles, you do a mole ratio. That's 2 steps. And then you can reverse yourself back to grams for 3 steps. So this will be a 3-step setup. I will go ahead and set it up now. So I don't count the given as a step, but there's step 1, 2, and 3. So starting off with here with our given information, we have 12 grams of silver. And the grams of silver has to be repeated here at the bottom. We said grams, we can go to moles next. So moles of silver. That's our molar mass. And when you look at molar mass, the numbers with molar mass, it is understood per 1 mole, and the grams comes from the periodic table. Silver's mass from the periodic, I wrote silver, and it's supposed to be copper. So I've already messed this one up. Just know I'm going to restart it right now. So I've erased my silver. I'm going to go back and put in copper. Copper is my known information. Not really sure what I put up there, but that should be Cu for copper. So getting back, I'm finding copper's mass off the periodic table, and copper is 63.55 grams per mole. So grams cancels, I'm left with moles of copper. That must go into my denominator, and that is moles of known. So moles of unknown must go on top. This sets up our mole ratio step. Our unknown is silver. That's where the question mark is. And the numbers here come from our coefficients. The coefficient with silver is 2. The coefficient with copper is an understood 1. Moles of copper cancels. I'm left with moles of silver. And we continue on, moles of silver here, and we can go back to grams at this point. So moles to grams of silver, and again, it's molar mass. So the 1 goes with moles, and the number that goes with grams is from the periodic table, and silver's mass from the periodic table depends on which version of the periodic table you use. But I'm going to write down 107.9 because I have another one that is 107.87. Moles cancels. We're left with grams of silver, and we are ready to calculate our answer. When you come up with your answer, you do need 3 significant figures in the final answer. Once you multiply everything on top, divide by any numbers that you see on bottom, final answer is 40.7 grams of silver. Something else to point out that I did point out verbally earlier is that point in which you change your substance. So as I look at this, the only point in which my substance changes is during the mole ratio step. So in this problem, my known was copper. All of my labels for the substance are copper up until the mole ratio step. And then I changed my unknown, which is silver in this problem, and it stays silver until I am finished. Because again, we can have problems that are more than 3 steps, especially if we have some SI conversions that need to happen, like milliliters to liters. Here's our last example. Again, you're making sure you write down the problems and then all the work. How many grams of copper are required to react with 1.5 liters of 0.1 molar silver nitrate? So we have 2 pieces of given information today, and both of these belong with the silver nitrate. So under silver nitrate, I'm going to write 1.5 liters. And then the 0.1 molar, remember I told you that molarity is really, if I can write, it's really moles per liter. I'm going to go ahead and write that as 0.1 moles per 1 liter, because that is how it should be written. So 0.1 moles per liter. How many grams of copper? So we are looking for the mass of copper. I see molar, that's molarity. I told you I wouldn't give you molarity and molar volume in the same problem. So if you're looking at your boxes, we're going to go from molarity to moles. Then while we're at moles, we're going to do a molar conversion and for our mole ratio step, and then we can go to grams. With the 2 pieces of given information like this, my suggestion to you is going to be start with the one that only has 1 unit associated with it. And the 1 unit associated with this is the 1.5 liters of silver nitrate. So 1.5 liters of silver nitrate, and we're ready to move on. Again, if I have liters of silver nitrate given, I need liters of silver nitrate down here, and I can go from liters to moles. Look back at your boxes, you will see that. So liters to moles. I'm still dealing with silver nitrate. I haven't changed my substance. Notice this right here. That is liters and moles. And I told you for molarity, that information would always be given. The 1 must go with the liters. And then in this case, with moles, our given number 0.10. I'm ready to move on. Oh, somebody got a little excited out in the hall. So back to this right here, we got moles of silver nitrate. And we will continue on with this. I'm going to put moles of silver nitrate there at the bottom. That is moles of my known substance, so moles of unknown must go on top, and that will be moles of copper. That sets up our mole ratio step. This is where we grab our coefficients again. The coefficient for silver nitrate is 2. Coefficient for copper is an understood 1. Those units cancel, and I'm left with moles of copper. Now we're ready to go back to grams, so we can go from moles to grams. Just trying to find a color here that'll work. So we've got moles of copper here at the bottom and grams of copper on top. Again, molar mass, it's understood per 1 mole, and the mass for grams comes from the periodic table, and copper's mass is 63.55. Again, that's from the periodic table. Multiply all the numbers you see on top. Divide by any numbers you see on bottom to get your answer, and our final answer is 4.8 grams of copper.